Now we'll be talking about maximum power transfer. So the idea is that if you have a load resistance connected to a part of the circuit, then you have a current I flowing into the load resistance. Now we know that I square RL gives you the power that is being absorbed by the load resistance. Now, how much power a load can drive from the circuit? So basically we want to find out the maximum power that can be transferred to this load resistance by this entire circuit that it is connected to. So now the derivation, the mathematical formulation is given here. So the idea is that the formulation shows you that the maximum power that can be given to the load resistance is when the load resistance magnitude of the resistance equals to the total circuit resistance that it is connected to. In other words, the total Thevenin resistance of the circuit that the load resistance is connected to. So now schematically, if we see in the figure on the left that we have a 5 ohms resistance, which is the circuit resistance connected to a 10 volt source. Now, if we vary the load resistance, what will happen is that if we increase the load resistance, the entire resistance in the circuit increases. So the current, of course, decreases as we see in the blue line here. The current decreases. Also, the voltage across the load resistance, it increases, which is shown by this red line. Now, at a particular point, if we see the power graph, at a particular point, the power increases, but reaches a maximum, then starts to decrease. All right. So, no matter if we keep increasing the load resistance, it will drive, it will increasingly drive power from the circuit, reach a maximum, then start to decrease the power it draws from the circuit. Now, at that point where it draws the maximum power is called the maximum power transfer resistance, and at that point the load resistance equals to the total circuit Thevenin resistance. The same thing we see if we have a different circuit resistance or different Thevenin resistance with a different source voltage. We see that as the RL increases, the voltage across it increases and the current through the circuit decreases, and the power that it absorbs increases, reaches to a maximum point and then start to decrease, and the point at which it draws maximum power is when the load resistance equals the circuit Thevenin resistance, which is equal to 50 ohms in this case. So that's the theory. Now, as an example, if you see this circuit, in this circuit we have a dependent voltage source and also an independent current source. All right, well, this is a voltage dependent voltage source. Now, we want to find out the value of RL, like what should be the value of the resistance RL such that it draws maximum power, right? Now, this follows directly from the maximum power transfer rule that the value of RL should be equal to the entire Thevenin resistance of the rest of the circuit, right? So the first things first is like we have to calculate the Thevenin resistance, and for that we take out the load resistance, and this is our net circuit. If you see that the resistance, the 4 ohm resistance is not given here because if we open the load resistance, it's open circuit. So the current going through this branch is 0. So therefore, what is the voltage drop across the 4 ohms resistance? It's 0 volt, right? 4 into 0 ampere, it's 0 volt, and which acts like a short circuit. Therefore, we just replace it with a straight wire. All right. Now, we have to find out basically the VOC, which is basically the voltage across the current source because they are in parallel right now. All right, so the main consideration is only this part of the circuit, which is a series circuit. voltage dependent voltage source, series with 4 ohms, series with a current source, series with a 2 ohms resistance. Now, if we see Vx, right? If we see Vx, Vx is basically, what is the value of Vx? Since we know the 2 ampere current flows goes to the negative terminal, so Vx is minus 2, which is the resistance, times 2, which is the current. So Vx is basically minus 4 volt. All right. Now, what is the magnitude of this 4Vx voltage dependent voltage source? Now it becomes minus 16 volts. Right? It becomes minus 16 volts. Now, what is the voltage drop across the 4 ohms resistance at the bottom? Since the current flows in the anticlockwise direction, the voltage polarity will be plus here, minus here, right? And the voltage drop across it will be 8 volt, right? So we see that we know all the voltages across all the circuit elements, right? Except the VOC. So if we apply KVL, clockwise direction inside the circuit series loop, we basically find out the VOC, right? And if we do that, we see that the VOC basically becomes minus 4 volt, because it's minus 8, minus 16, which is minus 24, and minus so it's minus 8 minus 16, right? So if you see that if we apply the KVL, it's minus 8, right? And then the minus is because of the minus of the voltage source, and the magnitude is minus 16, so it becomes plus 16, minus 16, right? It becomes plus 16 now, plus 16, and then we have plus Vx, but that is minus 4, so that means it's minus, right, is equal to VOC. So what is our VOC? It's 16 minus 12, right? It's 16 minus 12. Yeah, so this is plus, so this follows like plus VOC equal to 0, right? That's the actual KVL. So the VOC, if you take in the other on the other side, it becomes minus VOC is equal to 4 volt. So basically VOC becomes minus 4 volt. All right. So now once we get this minus 4 volt, that's the VOC. Now we have to find the Thevenin resistance, and for that, what we do, we have to find the short. We have to short the terminal across the load and find the short circuit current, because we want to apply the formula which states that R Thevenin is basically equal to VOC, right, divided by ISC. So it's open circuit voltage divided by the short circuit current. We know VOC, which is minus 4 volt. So now we continue with the same circuit with the open load, and now to find the short circuit current, we'll short this terminal, and the resultant equivalent circuit is shown here. All right, if you can see, it's shown here. Now, if you see that this wire short circuits the entire circuit, right? So the 2 ampere source, ideally it should split on the left and on the right, right? But since now the entire 2 ampere is short circuited, the entire 2 ampere flows into this loop, and no current goes on the left hand side of the circuit, because the short circuit has the lowest resistance, so the entire current will be flowing like this. So ISC becomes 2 ampere. All right, so this ISC becomes 2 ampere, right? So now we have our ISC, which is 2 ampere, right? We have our VOC, which is minus 4 volt. So what should be the RThevenin? VOC divided by ISC, which is minus 4 divided by 2, which is minus 2 ohms, right? So now this is our, the left hand side is our Thevenin circuit, right? And the right hand side is basically the load part of the circuit. Now note that here we add the 4 ohms, right? Because remember, these 4 ohms disappear because we opened the load resistance, and for which current flowing through the 4 ohms was 0, and that's why we neglected it. But nonetheless, when we'll add the load resistance, these 4 ohms will appear. So that's why the 4 ohm is appearing with the load resistance, and our RThevenin is minus 2 ohms, or basically it's this one. The RThevenin is minus 2 ohms. So now, what is our equivalent resistance? Now remember, the equivalent resistance means that the RThevenin should equal the R load, right? But since like resistance is a positive value, so we take the absolute term. So RThevenin is basically 2 ohms, right? So our RL should be actually equal to 2 ohms, right? Now this, our original RThevenin, mathematically it came to be minus 2, right? And these 4 ohms additionally came up because we removed the load. Now if you sum them up, you also get the 2 ohms. All right. So ideally, most of the cases you will not have this 4 ohms kind of resistance appearing. So in your case, RL should be equal to RThevenin, but in this special case, 4 ohms is coming up. So you have to make sure that the RL should be equal to the total resistance of the circuit on the left, and the total resistance is RThevenin, which is minus 2 plus 4, which is equal to 2 ohms. So in either cases, you will get 2 ohms.